Hello everyone, welcome to Tuteetute. Now we will see the questions related to the analog electronics. So first question is this one. So we need to find the type of the filter. So if you see here, negative feedback is available. Negative feedback. So this parallel connection of resistor 1K and capacitor 1 picofarad are given from output to inverting terminal of the operational amplifier, so that it is having the negative feedback. That is one thing. So for the filters, generally we will use the negative feedback. So here also negative feedback is there. So we need to find what type of filter it is. Okay. So band stop filter, low pass filter, high pass filter, and band pass filters are there. So we need to check which filter this one. Okay. So for example, if you are working at frequency is equal to 0, that means DC. Then capacitor the impedance offered by the capacitor is equal to 1 by j omega c. So 1 by 0, that means infinity. So impedance offered by the capacitor is infinity, means the capacitor is open circuited. So for 0 frequency, if it is open circuit, it is not existing. Okay. So we are working on that one. Because this is voltage dividing circuit, for the operational amplifier here large amount of impedance is there. So current is not entering inside the operational amplifier. So whatever the current is coming here, this current is flowing through this 1K also. So this input voltage is divided in between these two, and at this particular point, that means across this one, we will be having VI by 2. Voltage is VI by 2. Because here negative feedback is there, we can apply virtual ground concept for the operational amplifier. So here also we will be having the VI by 2 only. Okay, VI by 2 only. So if you calculate if you apply the KCL at this particular node, that is at a inverting terminal. So what we will get? KCL by the application of KVL. So VI by 2 minus VI by 1K, okay, plus VI minus V out by 1K is equal to 0. That 1K can be taken common, we can send outside. So what we got here? So sorry, here VI by 2. Okay, once again I am telling here VA by 2 minus Vn by 1K, that is this part. Next VA by 2 minus V0 by 1K, that is this part. Okay, here VA by 2 is Vi. That Vi is cancelled with this Vi. Here minus Vi is there. So we will get output is equal to 0. That is nothing but we are not getting output here for the 0 frequency. That means it is not allowing the low frequency. So it is not low pass filter. Okay, it is not low pass filter. Next we will check for the higher frequencies. If you take higher frequencies, so what we will get? The capacitor is short circuited. So capacitor is short circuited. The resistance in parallel with short circuit is not required. Okay, that will become 0 only. Sorry, that we cannot able to consider because no current is flowing through that one. No voltage drop, no power consumption. So no use of this one. Okay, so the short circuit is there like this. So here VI we are applying. Here again we will get VI by 2. The same VI by 2 will be available here also. So output is equal to VI by 2. That means output we are getting. So higher frequencies are allowed so that it is a high pass filter. Next question. Find the polarity of the operational amplifier input for negative feedback operation. So for the negative feedback operation, already they are saying that negative feedback is there. What are the polarities? If you see the options, they are giving for okay, A is positive, B is negative, A is negative, B is positive. Like that we have to tell the polarities of the terminals A and B. Okay, which is inverting terminal, which is non-inverting terminal. That is what we need to identify. So, but here the output of the operational amplifier is connected here to the NPN transistor, and it is base, it is collector, it is emitter, and emitter is grounded, so that it is in CE configuration. In CE configuration, and input to output, here input is there, here output is there for the CE configuration. In between these two, it is providing 180 degrees. That means already here negative is there, and this negative is connected to A. That means A is negative. That means B is positive. Okay, that is the thing we need here. Okay, so A is negative and B is positive. That is what we have here. Already 180 degrees is provided by this one. So that what we can able to do, 180 degrees is provided, that 180 degrees we are representing here. Okay. Next, what is the time period of the oscillation of V out? So for the output signal, what is the time period? That is what we need to check here. And this particular circuit, if you observe carefully, here this R3 is connected from V out to inverting terminal, and that is grounded through the capacitor. And here we have one voltage dividing circuit from output to non-inverting terminal. This is representing actually a stable multivibrator. For the stable multivibrator, the time period is given by 2RC into ln of 1 plus beta by 1 minus beta, and beta is equal to from this particular voltage dividing circuit we will get that one, that is R1 by R1 plus R2. Okay, so 1 plus beta by 1 minus beta if you calculate, 1 plus beta by 1 minus beta if you calculate, that is what we will get here, 1 plus beta, that is nothing but it will be added with this one, so that is 2R1 plus R2 by 1 minus beta. So R1 plus R2 minus R1 is nothing but R2, so it is equal to 1 plus 2R1 by R2. So 1 plus beta by 1 minus beta is nothing but 2R1 by R2 we got, that is available here. So ln of this one. Okay, but in this case they have given with okay, R1 and R2 only they have given. Okay, so this part ln of 1 plus 2R1 by R2, ln of 1 plus 2R1 by R2. So option B. Okay, in option B is 2, 3, 4 same thing is there. So rest of the part also we have to calculate. Here 2RC is there. So this R is nothing but this feedback resistor and its capacitor is this one only. So 2R3C. 2R3C means option 2 is the correct option. Next, what is the small signal gain of below circuit? So for this particular circuit we have the gain formula directly, that is gain is equal to minus GM RD by 1 plus GM into RS. Okay, so drain resistance, source resistance and transconductance values we have to use, but they have given transconductance value is infinity. So it is equal to minus GM, directly I am not substituting the infinity, RD value is 5K by 1 plus GM into RS value is 1K. Okay, now take GM as common in the denominator. So if you take GM outside, what you will get 1 by GM plus 1K. So this GM will be cancelled, and if you take now GM is very large, that is infinity, 1 by infinity is 0. So in the denominator you will get 1K only. In the numerator you will be having minus 5K, KK will be cancelled. So minus 5 is the correct option. Next, for the circuit below, find the value of the current Ix. Okay, where is this Ix? Here Ix is available, and if you observe this particular circuit, here input 4 volts is given for this inverting terminal and some feedback network is there that is connected in between output and inverting terminal. So that is nothing but negative feedback is there. So because of this negative feedback it can be working as the amplifier only. So what we need to calculate in the sense here Ix, since it is having the negative feedback we can able to apply the virtual ground concept, and here positive terminal is connected to 0 volts. So because of the virtual ground this inverting terminal is also available at 0 volts only. And if you consider, because here we need to calculate the Ix, I will consider this voltage is Vx. So at this particular node, okay, at the inverting terminal at this particular node we will apply the KCL. Okay, so 0 volts minus 4 volts, 0 minus 4 by 6K plus 0 minus Vx by 0 minus Vx by 3K. So it is equal to 0. Okay, this is a KVL application at this particular node. So what we will get here, minus KK can be taken common and we can send outside, that is 0. So we can take 6 is LCM here. So here minus 4 and minus 2 Vx is equal to 0. Okay, because here 3 is there, 3 2 is 6, 2 into minus Vx is minus 2x. So this is what we got here. Now minus 4 is equal to 2Vx and Vx is equal to minus 2. Okay, and Vx is equal to minus 2 we got, that Vx is equal to 3 times of Ix. So okay, minus 2 is equal to 3K times of Ix. So what we need here, minus 2 and that is 3K. So Ix is equal to, we will get minus 2 by this 3K, that is minus 0.6 milli. So we'll get option 4. Option 4 is the correct option here. Next, Q1 and Q2 are perfectly matched BZTs, assuming beta is to be infinite. So beta is infinite. This current again beta is infinite. Whenever we have beta is infinite, you can take base current is equal to 0. Okay, beta is equal to IC by IB. Since beta is very large, we can take base current is equal to negligible. Base current is equal to 0. So immediately we can able to take the current which is coming out of this particular, or the current available at the base, that is 0. The current available at this base is also 0, because that particular property is available for these two transistors Q1 and Q2. And forward bias voltage is of 0.7, find the I out. So here I out is there. This is what we have to calculate. Actually it is a current mirror circuit. So whatever the current is there this side, same current, same amount of current is there at I out also. That is what we have to calculate. Okay. So here supply 5 volts is there, and this particular junction is taking 0.5 PNP transistor. So here also 0.7 volts will be taking. So that at this particular node, if you apply KVL, 5 minus 0.7 is nothing but 4.3 is there. Same line, same voltage will be there, 4.3 volts. And this will take again one more 0.7. If you remove 0.7 from this one, at this particular node or across this resistor, how much amount of voltage will be there? 3.6. So here we are having 3.6. According to current mirror circuit, if you have here 3.6, here also you will be having 3.6 milliamps only. So option 3 is the correct option. Next, in the circuit below, find the terminals of X and Y for the circuit to be in negative feedback. Here they are not giving that it is in negative feedback. In order to have the negative feedback, what are the polarities of X and Y? Those things we have to calculate. So in order to have that one, how to tell that one? What is having? If it is negative feedback, okay, if it is in negative feedback, what is the meaning of that one? Here, for example purpose I am taking here, this is the operational amplifier. It is negative, it is positive. We can tell it is in negative feedback when you have here V minus is greater than V plus. The voltage at the inverting terminal should be larger compared to voltage at the non-inverting terminal. At that moment we can able to tell it is in the negative feedback. Okay, so we need to check that one. For that purpose, we need to compare the voltage at the inverting terminal, non-inverting terminal and voltage at the non-inverting terminal. Here they have mentioned it V, X and Y, so that we need to have Vx value and Vy value. Then we need to compare these two. Okay, so in order to compare that one, we will make here input is equal to 0 and here V0 is there, and this here what we will get, Vx will get, and here we will get Vy. Okay, so if you apply Vx, how to get Vx? It is actually no current is going inside. So here 1K, here one more K, here V0 is there. If you assume V0 is the supply for this particular thing, so V0 into 1K by 2K will get voltage dividing rule. So V0 by 2. So it is equal to, here Vy is there. Here anyway it is short circuited. Here 2K is there, here 1K is there. Again voltage dividing rule by the application of V0 as a supply. So this node voltage is nothing but voltage across the 2K. That is nothing but V0 into 2 by 3. Like this will get. So 2 by 3 is 0.6, 1 by 2 is 0.5. So Vy is larger compared to Vx. So Vy should be negative. Okay, this is negative, this is positive. Then we can tell it is in the negative feedback. Okay, so you can able to check the proper answer. Y is negative. So option 3 is the correct option. Next one. So what type of feedback in the below circuit? That is what we have to identify. Actually the circuit is simple circuit, that is the basic circuit, non-inverting amplifier. Okay, so input is given to non-inverting terminal and it is basic feedback circuit. It is given to negative feedback, negative inverting terminal. That's why this 1K is providing the negative feedback. Okay, so it is a non-inverting amplifier, but we need to identify what type of feedback is there here. Okay, what type of feedback is there, that can be told by observing this feedback element only. The feedback element is 1K, which is available in between output and inverting terminal. So this 1K is directly connected to the output terminal. Whenever directly connected to the output terminal, the sampling we can able to tell that is a voltage sampling. Okay, voltage sampling. Okay, but it is not directly connected to the input. Input is available at the non-inverting terminal, but it is not directly connected. So that based on this only we can able to tell what type of feedback is available here. Okay, so since it is not directly connected, it is a series mixing. Okay, and since it is directly connected to the output terminal, voltage sampling. Voltage sampling is nothing but we can take shunt. Okay, shunt sampling. So that series shunt feedback is available in this particular case. Next, bipolar junction transistor is field controlled, voltage controlled, current controlled. It is very basic question. So BZ is current control device. IC is equal to beta IB plus 1 plus this IC naught. We can take that one. Okay, so current control device, that is this one. Okay, so we can able to tell input volt by the variations in the input current, we will be having the variations in the output current. Okay, so based on that we can able to consider. So IC is equal to beta IB plus 1 plus beta into IC naught is there. Based on that also we can able to tell very simply. Next one is 4 microamps current flows through a conductor for 4 seconds. So they have given some current 4 microamps. Current is equal to 4 microamps. It is available for 4 seconds duration. Okay, and current is equal to charge by time. Okay, because IT is there, we can take immediately this particular relation. Find the number of electrons passed through the conductor. Okay, number of electrons we have to calculate. Okay, so how much charge? Q is equal to IT. So it is equal to I is nothing but 4 micro multiplied with T is nothing but 4 seconds. So it is equal to 16 micro we got. Okay, 16 microcoulombs. Actually, what is the charge of one electron? That is 1.6 into, okay, Q is equal to, for one electron, 1.6 into 10 power minus 19 coulombs. Okay, but now for 1 coulomb, how many number of electrons will be there? 1 by 1.6 into 10 power minus 19. That is 6.25 into 10 power 18 electrons. Okay, this many number of electrons will be there for 1 coulomb. Now, in this particular case, how many coulombs are there with us? 16 microcoulombs are there. So, 16 micro into, for 1 coulomb, how many electrons? 6.25 into 10 power 18. Okay, so this calculation we have to perform. So, what we will get? So, 6.25 into 16 I am performing here. So, 6 5 is 30, it is 12, 15, it is 36, 37. Multiplied with 6 to 5, so 0, it is 10, it is also 10, it is also 10. So after 2 points, that means 100. So 16 into 6.25 is nothing but 100, and here micro is there, 10 power 18 is there, that means 10 power 6, if you remove 6, you will get 10 power 12, that is 10 power 14 electrons. So this is the correct option. Next, average reading multimeter reads 5 volts when fed with a square wave symmetric about the time axis. Okay, here average reading means they are giving directly I average is equal to, they are talking about current. Okay, some square wave is there, so they have got average value. Okay, average value of this X signal, for example, square wave we got 5. Okay, symmetric about time axis. For the same input, what is the RMS value? Okay, actually average value formula is given by 1 by t integral over 1 period x of t dt. If you consider x of t is that square wave, and RMS formula is given by root mean, because square is there, here you have to take square. But for the square wave, what will happen means, whatever the average value is there, same RMS value you will get. Since they have given 5 volts, it is also 5 volts only. Next, what kind of filter is realized by the below circuit? Okay, so it is a standard circuit. Actually, by seeing this one we can tell it is all pass filter. You can able to check that one. Okay, take frequency is equal to 0, you will get output. Take frequency is equal to infinity, then also you will get output. But at these two frequencies you will get the phase difference is there. So all pass filter is actually passing all the frequencies, and it is providing the different phase shifts at different frequencies. Okay, that is followed by this particular circuit. For example, F is equal to 0, this particular capacitor will be open circuited. Okay, so if it is open circuited, here also this is inside is nothing but here no current is there. So no current is there means this is no use, because no voltage drop is there. So here also Vin is available. Here Vin is available means here also Vin will be there. So we can able to apply the KCL here, so you will get some output. If you take capacitor is at infinity, frequency is equal to infinity, so it is short circuited, 0 volts, here also 0, according to virtual ground, here also 0 volts you will get, some output you will get. So all the frequencies it is, we are getting the output, that is what we have to observe. So it is the all pass circuit. Next, a 3-phase diode bridge rectifier supplied from a 3-phase 400 volts 50 Hz AC supply delivers power to a resistive load of 50 ohms. The peak value of the instantaneous load voltage will be. Okay, it is RMS value. So RMS value is nothing but Vm by root 2, that is equal to, we have 400. So Vm is equal to 400 root 2. Okay, this calculation is simple. So option is this one. Next, find V out in the below circuit. Assume operational amplifier is the ideal one. So what we need to calculate? Just V out we need to calculate. Here V out. Here non-inverting terminal is already grounded. That means here 0 volts is there. Because of the negative feedback, virtual ground is there. So here we have to apply 0. So now you can able to apply here this KCL we can able to apply at this particular node. Or because here 0 volts is there, we can able to apply here this particular KVL we can able to apply. So this particular 1K, this voltage source and this 1K all are in series. So the current is passing like this. For example, that is I current is passing. So plus 2 minus, here plus 2 minus. So if you apply KVL in this particular loop, plus 1 minus I into 1K, okay, 1K also I am writing, next minus I into 1K is equal to 0. So 0 to 0 we have taken. Okay, so from this what did we get here? I1 is equal to 2 times of k into I. So I is equal to 1 by 2k. That is equal to 1 by 2 into milliamps. So this is nothing but I. This I is coming up to this point. But there is no path for this one to go inside because a large amount of impedance is there. So the same I should go through this 1k. Okay. So and this 1k is available in between 0 volts and V0. So what we can take here, 0 volts minus I into 1k minus V0 is equal to 0. So V0 is equal to what we can write here, minus I into 1k, and I is equal to, already we got 1 by 2 milli. So 1 by 2 milli into 1k. So we got here minus 1 by 2. Okay. So this option is not available in the given options. Okay. This answer is not available, but option is minus 0.5. It is voltage, that means volts. We'll get this one. Okay. Next one. Here, for the two circuits to be equivalent, okay, this circuit is already, they have equated to this particular thing. These two are equivalent circuits. What is the value of the R? R, where is this R is available? Here R is available. This R is not there in this particular case. But they are telling these two circuits are same. Okay, anyway, here gate is not connected to anything. That means here gate is open circuited. That means Ig is equal to 0. Since it is equivalent to this particular circuit, here also Ig must be equal to 0. Okay, that means in this particular path there is no current. That is what they are telling. Okay, that means whatever the current is there here, Gm into Vgs, this current is flowing through like this. So when this current is flowing across R, how much amount of voltage will get? That is Vgs, that is equal to, through R the current flow is Vm into Gm into Vgs. So this Vgs will be cancelled, and they are asking the R value. So R is equal to 1 by Gm. So we have got that particular option. Next, in the circuit below, find the V0 for the negative feedback. Actually, the same circuit we have seen previously. Okay, and we have what are the polarities we have taken to have the negative feedback. Okay, find V0 for the negative feedback operation. Here they are asking for the output now. Okay, so previously we got it is the negative terminal, it is the positive terminal. So with that one only we will continue with this particular problem. Okay, so what we need to have, it is having the negative feedback. So the voltage at this particular node will be equal to at this particular node. That concept we can able to apply. Okay, so it is Vy and it is Vx. We can continue now. So Vx is nothing but from the V0, voltage dividing rule we have to apply. So Vx is equal to, okay, Vy. So Vx value I am writing now. So V0 into, this is 1k, that is also 1k, 1k by 2k, that is V0 by 2. It is equal to Vy we need to write. But Vy should be written using this V0 and Vy should be written using 2 volts also. While writing 2 volts, you make V0 is 0 and I am writing with respect to 2 volts. Supply voltage into, where we are finding across 1k by, here we have 2 plus 1k, that is 3. Plus, next we need to calculate this Vy due to this one. At that moment we need to make 2 volts is 0. So that what we will get now, due to V0 I am calculating. So V0 into, we are finding across 2k, 2 by 3. This is what we will get. So it is equal to, 3 is LCM, and here we got 2 plus 2 V0 by 3, and here V0 by 2. Okay, so that what we can do this cross multiplication. 3 V0 is equal to 4 plus 4 V0. We can send this one this side. So V0 is equal to minus 4. So option 1 is the correct option. Okay. Next, MOSFET biased in the common drain configuration is best suited for designing transconductance amplifier, current buffer, voltage buffer, and trans resistance amplifier. Actually, common drain, it is a comparable to common collector configuration in case of BJT. Common collector is the buffer. Okay, common collector is having infinite amount of, a large amount of input impedance. So input voltage is equal to output voltage. That means here buffer. So here also same thing, voltage buffer. Thank you.